Hello. Today's lesson, the fourth of our unit, is going to focus on electromagnetic radiation. I'll remind everyone that our unit essential question is, how do the properties of subatomic particles determine the different chemical properties displayed by atoms of each element? And we'll kind of focus in more on two questions. How do studies of the atom reveal information regarding the way electrons interact with light? And then, how do scientists apply an understanding of this behavior to learn the composition of objects? In regards to the first question, we're going to look at some of the experiments conducted by Max Planck and Niels Bohr, really focusing in on the electrons and how they behave, as we said, interacting with light. And then the second question, we'll start to see some really cool applications of this knowledge that are used actually all over the universe. So I wanted to just give us some things that we should be able to do, some objectives. At the end of this lesson, you should be able to provide support and criticism from both sides of the wave-particle debate. We'll be able to calculate the energy carried by different types of electromagnetic radiation. We'll be able to identify an element based on its atomic emission spectrum. That might take a little bit of work in the lab as well before we fully have that one mastered. And then determine the composition of an unknown substance using atomic emission spectra data. And again, that may be a little bit with the lab as well. So the first thing I want you guys to do is take a look at the slide here at the picture, which is the electromagnetic spectrum. Now, you're not asked to write this down in your notes, but I think it would be a good idea anyway to write this down somewhere. So what you see is a line that starts on the left with gamma rays, X-rays, ultraviolet, visible, infrared, microwaves, and radio waves. Those are the different types of radiation that are produced. Now, there's different properties that waves can display. They have wavelength, frequency, and energies associated with that. And you can see then at the very bottom what the waves actually look like relative to each other. So on the left side, we have lots of up and down waves. So that means that there is a higher frequency or number of up and downs per distance right to left. There's also going to be a shorter wavelength over there. The wavelength is looking at the distance from peak to peak, so to speak. So on the left side, the peaks are very close together. As you move to the right, the peaks are much further apart. And then we'll look at some other calculations that are going to show us that the waves on the left carry more energy than the waves on the right. Now, if we think about our everyday lives, we have this type of electromagnetic radiation occurring all around us all the time. If you're driving in your car, you're listening to radio waves. We tend to characterize radio waves based on their frequencies. That's the digits on the dial. If you're listening to, 96.9 radio station here in Lancaster, or 101.4. These are all units of wavelength, units of hertz, or of how many waves are occurring per second. And there's a lot of them, as it turns out. But those are the lowest wavelength, or the lowest frequency, I should say, waves. A little more frequency, a little higher frequency waves, those might be microwaves. We might get to infrared waves. And eventually we get to this tiny little spot in the spectrum, which is all of the visible light we see. You might have heard the saying Roy G. Biv: red, orange, yellow, green, blue, indigo, and violet. And that's what you see in the center of the diagram here. So in order for us to see light, it has to have those wavelengths and frequencies. If it has a lower frequency, then it falls into the infrared range. A higher frequency falls into the ultraviolet range. X-rays are a little higher frequency, and then gamma rays have a higher frequency still. As far as just a couple really cool things about waves, most of you guys probably don't listen to AM radio, but there is another dial on the radio, and if you click the AM button, the AM signals are older signals, and these waves, if you're ever driving like under a bridge, the AM radio tends to cut out in those spaces because the waves are kind of too big and long, and they can't get within the bridge. So that's why we've switched to FM radio band, because they're higher frequency than the AM radio waves, and they're able to penetrate more under a bridge. Moving across the scale a little bit, we don't tend to be worried about radio waves and microwaves and infrared waves or even visible waves doing much damage. But we do worry a lot about ultraviolet rays, which come from the sun. The sun produces all sorts of different waves. It produces all the visible light that we see, but it also produces ultraviolet rays. We tend to categorize them as UVA or UVB rays, just like we categorize visible light as different colors. But the more energy the waves carry, the more frequency, or the higher frequency, the more damaging those rays are going to become. And there's basically two reasons for this. And if you look at the graphic below, this should become pretty clear. The ultraviolet rays have a higher frequency and carry more energy. So a wave that carries more energy, it makes sense that that could do more damage, but the wave is also able to penetrate much deeper. Just like the FM radio wave can penetrate under the bridge, where the AM radio cannot, ultraviolet rays can penetrate deeper into the skin than visible or infrared rays can. And they're carrying more energy. And of course, we know ultraviolet rays tend to cause cancer to develop in cells. Now, if we move to the next section of the scale here, we have X-rays. And X-rays are more energetic and have a higher frequency than the ultraviolet rays. This allows X-rays to serve the primary function that humans use them for, which is to conduct an X-ray scan. The X-ray is able to easily penetrate through skin and muscle tissue, but it's not high enough frequency to penetrate through the more dense bone that we have. And so X-rays give us a good picture of what bones look like, because it goes right through the skin and bounces off of the bones. Gamma rays would be even more energetic than that. So high energy and high frequency tend to cause a more damaging ray. So what is electromagnetic radiation? Well, electromagnetic radiation is wave-like energy with both magnetic and electric properties. If you take a more advanced physics class, you'll learn kind of more how wave-like energy with both magnetic and electric properties works. But for now, it's going to be good enough to just know the definition there. You could take class after class after class on the electromagnetic spectrum, on electromagnetic radiation. It's in so many different devices that we use. But for now, we're just getting a foundational knowledge. And we tend to measure waves in a few different categories. We measure wavelength, which is symbolized by this symbol called lambda, which is measured in meters or centimeters, or sometimes it's even measured in something like a nanometer if the waves are really small, which they usually are. Frequency is another important measurement. We just talked about that. That's how many waves occur per second. So you can see the unit there. The symbol is actually called nu. It looks like a V, but it's not. It's like a Greek letter here. But it's measured in hertz. And what does a hertz mean? It means 1 over seconds, or how many waves per second. And so sometimes it's designated as second to the negative 1 or 1 over seconds. Now, the first equation that I'm going to introduce today will also involve the speed of light. So we'll note that it's actually 3.00 times 10 to the 8th meters per second. So if you're writing that down, I would just add the 2 zeros after the decimal. 3.00 times 10 to the 8th meters per second. That's pretty fast, as it turns out. Think about, if a car is traveling really fast, it might be going like 30 or 40 meters per second. And 3 times 10 to the 8th is around, I think, 3 billion, if I'm not mistaken here. Might only be 300 million meters per second. So that's very, very fast. And the equation we have is that c, the speed of light, equals lambda times nu, the wavelength times the frequency. What's really cool about this is, and if you were to plug in like ones for all of these numbers, if I said that c equals 1 times 1, well then it's 1. So 1 equals 1 times 1. If I increase lambda, if instead of having lambda be a 1, I make it a 2, then in order to keep c as 1, I have to shrink the frequency. And what that's saying is that wavelength and frequency are inversely related. And you see that's the next point. Frequency is inversely related to wavelength. If I increase the wavelength, and I have to keep c constant because it's the speed of light, it's a galactic rule here, or a universal rule, c will always be the same thing. So just pretend it's a 1. If c has to equal 1, and I increase lambda, which is the wavelength, then I have to decrease the frequency. If I go back to my electromagnetic spectrum picture, that makes a lot of sense here. On one end, you have the long wavelength with the low frequency. On the other end, the short wavelength with the high frequency. And the last point then, or the last part of this, is a question for us to solve, a problem. Calculate the wavelength of light emitted by a lamp if the frequency is 6.20 times 10 to the 14 hertz. So I know that c is 3.00 times 10 to the 8th meters per second. And then I have to rearrange my equation here. So if c equals lambda times frequency, I'm going to have to divide frequency to the other side because I want to get lambda by itself. So lambda equals the speed of light divided by the frequency. You will have to be able to manipulate equations in this class frequently. So if you're having any trouble at all with that, please ask. We'll have some opportunities to practice this. But lambda equals the speed of light over frequency. Then I'm just plugging the numbers in. 3.00 times 10 to the 8th meters per second divided by 6.20 times 10 to the 14th hertz. If I do the math, that's going to give me 4.76 times 10 to the negative 7th. And as we're going through problems, my strong advice is to try to pause the video and then solve the problem. Then listen to me go through it and see if your answer is correct, because it's easier to follow along as I do the problem than it is to do it on your own. The other thing that I think is important, and I haven't included it yet, but we always have to be thinking about units. So in this case, you do the same math with units that you do with the numbers. I took 3.00 times 10 to the 8th. I divided by 6.20 times 10 to the 14th. And always make sure you're plugging it into your calculator to confirm you're actually getting it to say the same thing that I did, 4.76 times 10 to the negative 7th, or something very similar to that. Then we have to figure out the units here. So if I take meters per second and I divide by hertz, well, hertz is 1 over seconds. So I'm taking meters per second and I'm dividing by 1 over seconds. That's going to be the same as multiplying by the reciprocal. So meters per second times seconds, the seconds cancel out and we'll be left with meters. And that's very good because wavelength is measured in meters. So we have 4.76 times 10 to the negative 7th meters. One last little tidbit I'm going to add here is when you're dividing these numbers, the 3.00 times 10 to the 8th divided by 6.20 times 10 to the 14th, remember in math you guys have learned about handling exponents. When you divide exponents, you're really going to subtract the numbers here. So I'm going to take 8 minus 14. Now that's going to give me negative 6. And if you look at my answer, the power is to the negative 7th. You might be thinking we made a mistake, but you have to look at the numbers. 3 divided by 6 is going to be less than 1, so that is going to shift my answer. It should have been something to the negative 6th, but through the math, we're going to move over a decimal place. The only reason I say that is, let's say your answer was 4.76 times 10 to the positive 7th. That should tell you you probably made a mistake, because if you look at the exponents, that's not what it should be. If you're close, if you're negative 6th, or, well, we said it should be a negative 6, so if you're at either a negative 7th or a negative 5th, that's probably right. You can check that as well. But just be aware of how to handle exponents, because it's easy to make mistakes in the calculator when typing these problems in. All right, so we'll move ahead. The next thing I want to talk about is the idea of whether light is a wave or a particle. And in the early 1900s, all the scientists were talking about, is light a wave or is light a particle? I want to talk just about some properties that waves tend to display. If a wave is moving in one direction, it tends to, imagine you're looking in a mirror here. Light is going to sometimes reflect, and that's what this picture is showing, is that from the top left corner, a beam of light is shot through the air and it hits the glass at an angle. That light can reflect, and if you look at a mirror, especially if you take two people, like the idea that you can see someone else in a mirror only when they can see you, that's because the light has to be able to hit at an angle that it reflects to you. And we'll do a demonstration of this in class if you remind me tomorrow to look at it. Also, though, we see refraction. So the light wave, when it hits the glass, some of it goes through the glass, goes straight forward, but it typically tends to bend. And the reason for that is, if you think about the light beam hitting the glass, the speed of light does change depending on the substance the light is traveling through. So we've been looking at the speed of light in a vacuum, the 3.00 times 10 to the 8th. It's a little different in every substance that it's traveling in. And when it goes from air to glass, the light slows down. But when it's traveling at an angle, if you're following the light beam, the right side of that light beam is going to hit the glass first. And it's going to slow down while the left side of the light beam speeds up. And it's going to basically turn the light beam further to the right in that moment. And so that's what we talk about when we talk about light being refracted. So those arguments support that light behaves like a wave. But we want to get into some other more difficult experiments, I guess, that shed some light on light, saying that it might be more like a particle. So there are two properties of light that could not be explained by wave theory. And that was the emission of visible light by matter. So sometimes matter seemed to just be kind of sitting around and it would emit light. The other thing is the absorption of light by matter. So sometimes matter is just sitting around and it absorbs light. Now, the atomic emission spectra argues that ground state electrons will gain a quantum of energy. And what a quantum means is like a tiny packet. It's the smallest amount. I had talked about how television isn't really continuous. It's just a bunch of pictures that are shown fast enough so it looks like it's one continuous movement, but it's really just a bunch of pictures that are still. And the quantum is like the individual picture. It's the smallest amount that's possible. So when they gain that quantum of energy, the smallest amount of energy possible, the electrons will jump up in the atom to an excited state. Immediately, the excited electron releases the absorbed energy as colored light, and it falls back to the ground state. When passed through a prism, the light is going to separate into distinct, discontinuous lines called the atomic emission spectra. So that's how we get these different colors. Now, what we're really saying here is when an atom absorbs light, that light comes in, it hits the electron, and the electron can move up a rung or down a rung, down an energy level, I should say. But if we have more than one atom in a sample, which we almost always will, there'll be many, many, many atoms, the light can be moving the electron to different places. And based on the energy rings and the number of electrons in an atom, each line is going to correspond to an exact frequency of light emitted by the atom. And there's usually just a few lines that are unique for each element. So we can determine what element is present when we look at the atomic emission spectra lines. And this is how we determine the elements that are in stars. So if you look across the universe, we've never been to many of these places. Even the planets in our solar system, we've started to send shuttles, but we knew the elements that made those stars up long before we got there because of the atomic emission spectra being produced by their atmospheres. So this is how we know what elements are in different stars or planets, and we will look more closely at the sun as part of our lab. We won't actually be looking at the sun, but we will look at how scientists analyze the sun and other stars. Now, I want to talk about a couple other concepts, and this is really getting at light behaving like a particle. The first is the photoelectric effect. The photoelectric effect is where photoelectrons are ejected by metals when light of a specific frequency shines on them. And the photoelectric effect was discovered by Max Planck. In fact, you're going to see his equation there. The energy, in this case carried by the photon, is going to be equal to Planck's constant times, look at that, that's nu, that's the frequency of the light. And now this picture shows us a lot of information. In the red, we can see a beam of light shot at this metal sample. And it's shot at 1.77 electron volts. That's a specific amount of energy that it's carrying. And that energy is not enough to knock an electron off of the metal. But the green light here, we see that's at a lower frequency. Now it's at, instead of 700 nanometers, it's at 550 nanometers. But we've got a higher energy here, 2.25. So as we increase the energy being carried here, we are going to now see an electron moving away from the metal. So that photon has enough energy to shoot out or eject an electron from the metal. In the blue, in the final stage here, this is another beam of light. It's at an even lower frequency, so it's got even more energy, and that's just according to the equation. The lower the frequency, we should have, and remember that when I'm saying the lower the number there, that's actually a higher frequency. So that was something that could have been confusing. Remember that by decreasing the nanometers there, that's actually the wavelength. So I misspoke. The 700 nanometers is a wavelength. The 550 then is a lower wavelength, and the 400 is an even lower wavelength still. And we'll do some calculation problems to practice that. But now we have a higher energy, and as we increase the energy the photon's carrying, we're going to see that now the electron that's being ejected is traveling faster. So two things we want to note here. The threshold frequency is the minimum energy needed to eject electrons. And that really aligned up with the idea of a quanta, this minimum value that's possible. Without that amount of energy, the electron cannot be ejected. Now, excess energy causes the electrons to travel faster, which we're seeing. And then there is a third point here, and that's increased intensity of light. Now, we haven't talked about light intensity yet, but it causes more electrons to be ejected. And basically, when I talk about an increased intensity, the properties are going to stay the same, but there will be more photons being shot towards the metal. So as we shoot photons towards the metal, if they're at the same energy, then the increased intensity won't change the speed. It will just change the amount of electrons that are being removed. And this really suggested to scientists that, well, light probably isn't a wave. Light is maybe more of a particle, because it must take a particle hitting these metals to knock out the electrons. And if the particle isn't thrown in fast enough, it won't eject any electrons. And the more particles that hit, the more electrons are ejected. Max Planck did some other work here. He also proposed that hot objects lose energy discontinuously in small specific amounts called quanta. So we think that something hot cools down continuously, but Planck says, no, that's not what happens. They discontinuously lose heat. It's just such small amounts of heat and so constant that it seems like, oh, the hot object is cooling down continuously. Just like what we talked about with the camera, or with the television being made up of just photo, photo, photo. A cooling object is made of quanta of energy, and then it's losing that energy, so it's cooling down. So therefore, he says that light behaves as particles called photons, which are like packets of energy containing a specific quantum of energy. So between his work with, it's technically called black body radiation, but that's just how objects lose heat. That's the field of study for that. And then also his work with the photoelectric effect, he comes to this conclusion of his equation, E equals h times frequency. He has his Planck's constant, which is 6.626 times 10 to the negative 34th joule seconds. So this quanta amount is a very, very, very tiny amount, but he's saying that is the minimum amount of energy, essentially, when you plug in different values for frequency that can be produced. So now we're going to do another example problem. We're told that purple light with a wavelength of 4.30 times 10 to the negative 7th meters, and we're asked to find the frequency and energy. Notice how I've done this. We're given wavelength. Planck's equation doesn't have wavelength in it, but we do know that the speed of light equals the wavelength times the frequency. I've substituted a v in here for the new, just it makes it easier to type it into the computer. We're going to rearrange that equation. Now we're going to have to solve for frequency, which is the speed of light over lambda, and then we plug the numbers in. 3.00 times 10 to the 8th meters per second divided by 4.30 times 10 to the negative 7th meters. That's going to give me 6.97 times 10 to the 14th. Let's check our exponents here. 8 minus negative 7, so that's 8 plus 7, that's 15. 3 divided by 4 should be a number smaller than 1, which is going to shift us to the smaller side. So the exponent was going to be times 10 to the 15th. Now it's times 10 to the 14th. So that really is matching up well with what we got as our answer here. And as far as units, meters over seconds divided by meters. Meters are going to cancel out, but the seconds are still on the bottom. So the answer is not seconds, it's 1 over seconds, or seconds to the negative 1, or you could call that a hertz, Hz. I'm going to call it 1 over seconds because I know I'm going to need to plug this right into my next equation. E equals h times v, or E equals Planck's constant, 6.626 times 10 to the negative 34th joule seconds, times 6.97 times 10 to the 14th hertz, or 1 over seconds. The way I have it written here, we see that the seconds cancel easily. My unit will be joules for my final answer. And then 6.626 times 10 to the negative 34th. So negative 34th times 14. So we don't want to multiply those. We want to add those exponents in this case. So negative 34 plus 14, that gives you right around negative 19. And so this answer seems to make sense for me. And that's in joules, as I said, for energy. So we have the frequency and the energy of that wave of light. And in 1905, Einstein's equation equals mc squared. It held true for all the electromagnetic radiation, no matter what the source. So what I'm trying to say here is Einstein and Planck, their work that they did separately, agreed with each other. And that's always good in science, that if one person's just saying something, it might not have that much weight. But when someone else, then another respected scientist, gets a similar result, now we're looking at that carries a little more weight with the scientific community, because their research is in agreement. So scientists are constantly checking on other people's work, trying to redo experiments in a different way, seeing how their work aligns. And the fact that Einstein's and Planck did align really strengthened both of their arguments. So to summarize, if you're supporting light as a wave, we want to be talking about things like reflection and refraction and diffraction, which you saw earlier in the video. For light as a particle, we want to be talking about the photoelectric effect and atomic emission spectra. Now, I know that you guys probably have a lot of questions about this, so come into class tomorrow and ask these questions. Why does reflection, refraction, and diffraction support the idea that light is a wave? Why do the photoelectric effect and atomic emission spectrum support light as a particle? I know that I said these things, and you can probably repeat after them, but I really want you to try to make sense of it. And so if it doesn't make sense right now, that's good. It shouldn't make sense. This is stuff that Einstein and Planck spent years looking at. So the idea that we can get it in a 15-minute video, that's a lot to ask. So come in with questions tomorrow, asking me to kind of prove that and make sense of it for you guys. And I have a couple challenge problems here that I'd like us to work on. So we have a cell phone relying on microwaves with a wavelength of 9.75 times 10 to the negative third meters. We want to know how much energy that wave carries. And then we have a UVA ray with a 3.54 times 10 to the negative 7th meter wavelength and a 7.94 times 10 to the negative 12th meters wavelength. I think it's a good idea to pause the video, and then I'll put up the work for the answers, and then you can check it. So I'd pause the video, do it yourself, and then check the answers. So as we go through the questions here, in each case, you're going to have to start with C equals lambda times V, the wavelength times the frequency, and you're going to have to rearrange to solve for frequency. And so in the first problem, I took the speed of light divided by the wavelength number that we were given, and we calculated the frequency. And then I'm going to plug the frequency in times Planck's constant, and that's going to give us the energy in joules. Now, the other problems are really the same type of thing. What's going to be interesting is the comparisons that we can do when we get done. So if we look at these three waves, my question for you here is which of these three waves would potentially cause the most damage to living tissue, and why? So hopefully you had a chance to kind of answer that question, but in this case, we'd expect the gamma ray to have definitely the most damage to living tissue. It's got the lowest, the highest frequency, the lowest wavelength. So those waves can penetrate much deeper with the low wavelength and the higher frequency. But then this also carries much more energy. Now, one other thing I'll talk about a little bit is that a lot of times people have questions of, are cell phones causing damage to human tissue? And I don't know the answer to this question. Scientists have looked at it. I've read a few studies, and some think it does, some think it doesn't. I don't think there's a lot of strong evidence to support cell phones causing damage due to the waves that they carry. And the reason is because these are microwaves. So if you look at the energy numbers, um, the energy carried there is 2.04 times 10 to the negative 23rd joules. And for the gamma ray, it's 2.50 times 10 to the negative 14th joules. That's about let's see here. I think it's about a billion times. I think it's about a billion times less energy than the gamma ray. So, just because they're carrying electromagnetic radiation, it's a very low energy radiation. And also, then when you look at the frequency, there's a much bigger difference. I mean, those waves are not going to be able to penetrate the way gamma rays would. So we'll wrap this up just talking a little bit about some other theories. De Broglie's wave-particle duality. All matter demonstrates characteristics of both waves and particles. This is an important kind of unifying principle. De Broglie says, I think everyone's right. We're debating whether light is a wave or a particle. Light behaves like both a wave and a particle, and in fact, so does everything. We just can't tell. Everything follows these rules that we call quantum mechanics. And quantum mechanics sounds really scary. It sounds like this advanced physics class. But what it means is, just like when you watch TV, it's not really video. It's really picture, 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 just shown really quickly so they look like a video. Well, matter and light really, it behaves like both a wave and a particle. It's discontinuous is the word that we've been using a lot today. Heisenberg's uncertainty principle then said that it's impossible to simultaneously detect both the position and the velocity of an electron or any other particle. And this was found by photon bombardment. Sounds scary again, but what it means is just launching photons at matter, and any attempt to locate the electron with a photon would cause it to veer off course. So basically, it was impossible to hit the electrons with these photons, and so Heisenberg figured that there's just too much energy being carried in this system, and we can't know the position and the velocity of an electron or any other particle. So as we get a little more advanced, we're going to talk about electrons as being likely to be in a region of space. It's not like a planet where we can see it orbiting the sun and say, well, tomorrow it's probably going to have moved here, because we know its position and we know its velocity, we know where it's going to be. We can't predict where an electron is going to be, but we can't predict exactly where it's going to be, but we can predict regions of space where it's likely to be. And so we'll see that. So it's a fundamental principle then for understanding light and matter. Schrödinger develops an equation that treats electrons as waves. This is essentially taking quantum mechanics a step further. It mathematically describes the wave properties of electrons. And the thing that Schrödinger did is he was able to explain the behavior of all atoms. Niels Bohr really just looked at hydrogen because it only has one electron. It's the simplest. Schrödinger basically expanded math, expanded our knowledge of math to describe these wave properties. So in some ways, what Schrödinger did is kind of like Newton, discovering calculus, and certainly Schrödinger used very advanced math concepts for this. And he describes the probability of finding an electron within a certain region. And those regions are called orbitals, the region around the nucleus where it's most probable to find an electron. So we'll dive into quantum numbers tomorrow, and I'll probably start with Schrödinger as kind of a bridge between the wave-particle duality we talked about today and quantum numbers, which is probably a more usable concept. So we'll get there tomorrow.